recording is rolling. So welcome to new week. You guys remember last week we were talking about forces, Newton's laws of motion. I did a bunch of free body diagrams with you guys. Talked a little bit about friction, Hooke's law. It's all fun. And I do want to get you guys' quizzes back to you. I'm still waiting on a couple. That's true for each of my different classes. So you guys check focus, make sure all your grades are up. If you're missing something, and okay. So let's get all in because I want to get those papers back to you guys. Now, last week I did assign you guys some problems, but I was okay. So short story of that. When I was originally put this unit together over a week ago. I was shopping off what I did the previous year, and I wrote those problems down. Okay, well, those are probably some pretty good ones because they were good last year. And I was looking at those over this weekend, just a couple days back, and realized, I'm actually teaching this a little bit different, and so those were not the best problems to choose. So I came up with some with a different set. Now, if you already did the ones that I assigned to you from before, then that's perfectly fine. I'll take those. I'll give you points. In fact, that would actually give you an advantage because you'll have seen some additional ones that maybe I wouldn't have run over in class otherwise. So that would actually just be good extra practice. I mean, I guess if nothing else, you guys got some extra practice problems to choose from. But if you guys want these, it'll help you guys out too because I know I don't like to change numbers on you guys, but these really are, I think, a better set of problems. You guys see clipped to the front of your desk. There's a tiny slip of paper. Flip to the front of your desk. Okay, so those are listed there. Just help you guys out a bit. I don't know if I'll do this every time, but since I'm changing problems, so give you guys that. Okay. But same deal as before is that there's a main homework, which is these that I'll pick up, and I will go over a bunch of these problems today and tomorrow. So that's the agenda for today and tomorrow. Do a bunch of book problems. There's also a bonus assignment. If you don't do the bonus assignment, it's not going to hurt you. If you do the bonus assignment, turn it in, then I'll give you extra points. So same deal as before. And debated over the weekend, should I do a bunch of labs with you guys first and then book problems? But this is what we're doing. We're doing a bunch of book problems today and tomorrow. And then I've got a series of labs lined up for you guys that we'll do into next week, including friction lab. I'd like to get an FRQ in, but we'll see how that goes. But before we get to all the physics stuff today, I got this yellow ballot in my mailbox this morning for Teacher of the Year. And I always have one day to get this done, just today. And there's always this activity that I do with students because, well, I don't know who the best teachers are, but you guys do. So I want to give you guys a vote, and then I'll do this for all my classes, and then get an idea by the end of the day which box I'm going to check, which teacher. Now, and actually the reason I do this too, besides to give you guys an opportunity to elect Teacher of the Year, is because I want to talk about voting systems. There's a science of voting systems. It's like a whole branch of study. There are many different kinds of voting systems out there, and there are different ones for depending on the type of election you're running. Is it like a single candidate type election, or is it like a legislative body? Anyway, but I just want to narrow it down to two systems and contrast these systems so you guys can learn a little bit about science of elections. So actually, I should ask you guys, do you guys know what first past the post is?
Yes.
What is that?
Oh, is that like electoral college? Like once you hit a certain
votes?
Yeah,
Electoral college is another layer on top of all this stuff, but stay away from that. But yeah, what do you think?
It's basically just whichever candidate in the end has the most votes.
Yep, that's it. Who has the most votes? So the idea for first past the post types voting system is that you might get a list of candidates, just like these 5 right here. You go into the ballot box, you vote for one, and then at the end of the day, whoever has the most votes wins. Okay, so that sounds pretty simple and straightforward and fair, right? Except, actually, it's terribly flawed. And I'll give you guys an example why. So suppose, I'm just going to make up some numbers, that maybe Mr. Egan gets 40% of the vote, and then Ms. Hudkins gets 20%, and then 20%, and then 10 and 10. So it goes 40, 20, 20, 10, 10. Right? Something like that. In that case, who got the majority?
Mr. Reagan.
No. What's the definition of majority?
Oh, majority. No one.
Yeah, nobody got the majority because majority you need more than half, right? You need more than half. The idea being that what if okay, so suppose Mr. A gets 40%. That means the other candidates collectively got 60%, right? What if they had maybe preferred one of these teachers, their voters had preferred one of these 4 teachers over Mr. Egan, for example, right? Something like that. The idea is that you would be splitting your vote, and you would actually be hurting what you would be your interest. You'd actually be voting against your own interest. So some of the terms that come up with us are strategic voting. So if you're in a first past post type voting system, you have to vote strategically. So it's not just who do I think is the best candidate. Now you have to start to think, well, how is everybody else going to vote? And I really like this candidate, but they're probably only going to get a tiny number of votes. So I'm probably better off not wasting my vote and voting for one of the two is probably going to win. Another term you hear with this is called the spoiler effect. So very similar idea. Say there's a candidate that you really, really like, but you know is only going to get a few number of votes. Well, if you go ahead and vote for that candidate anyway, you're effectively throwing away your vote, and then whoever who had a realistic chance of winning based on everybody else's votes, well, you would effectively not be voting for who was the closer of the two in your own preferences. You would actually be hurting your own voting interest. Pretty much all of the elections in the United States are run using this system, and this is aside from Electoral College. That's another layer on top of this, but all our systems are pretty much what I just explained. Okay? And that also creates an environment that really realistically only allows for two parties and doesn't really allow a lot of competition. Okay? Now, there are some alternatives to this, and here's just the one I want to talk about. It's called ranked choice voting, which also goes by the name instant runoff, and you'll see why after I explain this to you guys. So with the ranked choice system, what you do is you go to the ballot box and you actually rank your candidates. So you say, okay, maybe like Mr. Egan number 1, and then Ms. Page number 2, Ms. Hudkins number 3, and you can stop ranking whenever you want. So if there's like 50 candidates and you only care about like 3 or 4 of them, then you can just rank those and just like walk away. Right? You don't have to do all of them. But see, what that'll do is if there's someone that you really, really like but doesn't really have that good chance of winning, you will effectively not be throwing away your vote. Right? There's no spoiler effect. Right? So you're free to express your true preferences, and then behind the scenes, there'll be, say, a computer system that tallies up all the votes, and if there's no majority, it'll throw out the least popular candidates, and then their voters' vote will be routed to their second choice, right? And so like that, until there actually is a majority. Right? So it's a much better system. So we're going to vote with this style system called ranked choice or instant runoff voting. I wanted to do this with straw poll online, but the site is down right now, so we're just gonna have to do a hand count. Right? So I'll ask for a hand count for each one of these candidates, one by one, each one of these teachers. Now, keep in mind, since we're using a ranked choice style system, if you are the only person voting for one of these teachers, go ahead and vote for them, because it's not gonna count against you. Remember, there's no such thing as throwing away your vote in this style system, because if somebody gets a majority, it wouldn't have mattered anyway. And if nobody gets a majority, then what we do is we throw out the least popular and then just revote until there actually is a majority winner. Okay? Any questions so far? All right, so let's try this out. All right, so get your guys' card. All right, here's 5, you guys. All right, so votes for Mr. Egan. Who's voting for Mr. Egan? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like 10. 10 votes for Mr. Egan. Who's voting for Miss Hudkins? Miss Hudkins. Miss Hudkins. All right, so, okay. She gets some votes sometimes, but. Mr. Ortiz. Mr. Ortiz, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Voting for Miss Page. Miss Page. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh. And Mr. Torres. Mr. Torres. Okay, yeah, so it's popular in some classes, but. All right, so we're looking at something like this, right? So obviously the candidates that got nothing, but that doesn't really help their down very much. So I'm gonna have to throw out this page, and now it's just gonna be a 2-person race between Mr. Egan and Mr. Ortiz, right? You see how that works, right? Okay. Now, how this would actually work out in real life is that you would only go to the ballot booth once, you rank your candidates, and the computer system automates this whole process behind the scenes, right? So it's effectively like having like multiple primaries, right? Just automated. Right? So we're behind the scenes now. Right, so you guys get to either vote for Mr. Egan or Mr. Ortiz. So who's voting for Mr. Egan? Mr. Egan. I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Oh, right? Okay. Who's voting for Mr. Ortiz? Mr. Ortiz. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17. Yeah. And somebody decided to switch over and vote for the winner. Yeah. How it goes. All right, so Mr. Ortiz wins this class. That's how we're doing so far. We got, all right. Yeah, he's been pretty popular in my classes so far, so, all right. We got, put that aside. We need to do some physics problems. So pull out, see, chapter 4. Now the new set I chose, I skipped past the warm-ups, although these are all good problems. If you want extra practice, you got plenty of extra practice, but just want them doing in class. I'm gonna start with number 2 on the main problems. It says a football punter accelerates a football from rest to some speed during a time that the toe is in contact with the ball, which is a tiny fraction of a second. If the football has a mass of half a kilogram, 0.5 kilograms, what is the average force exerted on the ball? Nice warm up at the beginning of Monday. So this is number 2. Now I'm going to change the numbers in my notes so you guys have one more additional example you can follow, but the numbers will be pretty close. So, oh yeah.
Is this one of the ones we're supposed to do for homework?
Yeah, I'm just doing this set right here.
So, how do we know, there's 2 number 2s, so how do we know what
Oh.
to do?
Okay, yeah, you're right. So there's, okay, you're right, there are 2 number 2s. So the first number 2 is under a section that says warm-up exercises. Right, so we're skipping that one. And I'm just gonna skip all the warm-ups just for the class problems. I'm gonna go straight to this page here, so say football punter. Okay? Okay. So, see, there's this football. Okay. There's gonna be a, ooh, you know what? Football has an, let's check something right here real fast. Yeah. Okay. But let's I guess if you want to get real technical about this, you could include the weight of the football and then find the net force, whatnot. I'm gonna keep this pretty straightforward and say that maybe this is approximately a horizontal sort of kick, and that the weight of the football is not going to affect it very much, like negligibly. Right? So I'll do F sub kick. Let's do like a real straightforward interpretation of this, like the simpler interpretation. So the mass of the football is 0.50 kilograms. We're trying to figure out what is the kicking force, so that, see, the initial speed of the ball was 0 meters per second, it was at rest. It leaves the punter's foot at, okay, here's where I'm going to make up my own numbers. I'll say 20 meters per second. And let's say the time of contact with the football was like 0.15 seconds. Okay? So suppose those are your numbers. Can you solve for the average kicking force if you know you have to take this football of this mass up to this speed in this much time? Okay? You know what I'm thinking is, this is probably going to, at some point, route into Newton's second law of motion, right? This force is equal to this mass times the acceleration. But the acceleration, ooh, isn't that going to be kinematic? Right? So we have to go back to last section, all this kinematic stuff. Which of these 3 amigos looks like it's going to lead us to the promised land? First, second, or third? I like the second one. Yeah, got 2 velocities, solve for acceleration, got a time. Yep, that is the best one going right there. So let's go final velocity equals initial velocity plus AT. Okay. We're getting up to 20 meters per second from rest. And trying to figure out how much it accelerates, because remember, once you get that, then we're going to kick over to Newton's second law of motion. This took 0.15 seconds. See that? Okay. So it looks like this is one algebra step. I'm just going to divide both sides by 0.15 seconds. What is 20 meters per second divided by 0.15 seconds? I'm looking at an acceleration of, ooh boy, 133 meters per second squared. Yeehaw. Well, I mean, it is being kicked, right? Hey, guys, how many Earth G's is that equal to? Huh? Oh, well, yeah, about 13, right? Could you guys, this is a side note, this is not actually part of the problem, but you guys could do, say that there are about 10 meters per second squared in every 1 Earth G. Okay? You guys know we're in 1 G right now, right? Just sitting in this room. If you were floating around in space, it'd be 0 Gs, and this room is 1 G. And Yeah, this football is being kicked with about 13 G's. Well, G's is really like an acceleration. There you go, different way to okay, but we need to figure out what is the force on this ball. So let's go over to Newton's second law of motion. No, this is really the net force. So again, I'm just ignoring the weight of the football itself. Let's just do F equals ma. Okay. We got this acceleration, and the mass of the football was 0.50 kilograms. That mass being accelerated that much, what force was required to do that? I'm looking at 66.7 newtons. I just make up these numbers from scratch, but there you go. About 67 newtons of force to make that ball of that mass go that speed with that kicking time. Execute order 66. Right. Number 7. Next one, number 7. Right, I'm just going down this list. So as long as you follow along, you're gonna be all right. Okay. Changing the numbers. A 75 kilogram, or well, I'm gonna change his mouse too. But a man with some mass is standing on a scale in an elevator. Ooh. Notice that as the elevator rises, the scale reads some different force value. What is the acceleration of the elevator? Didn't you guys see a video of this last week? You guys remember the guy standing in the elevator? He had the camera trained on the scale, and as the elevator is accelerated up or down, that scale reading changed. Sometimes there's a little bit more than its weight, sometimes a little bit less. I want to do this with you guys. I'm gonna derive a formula for force reading from a scale in an elevator, and I'm gonna do it 2 ways. So split the paper in half and do landscape. I'm just giving you guys the notes this way. You guys can do whatever you want in your own notes. First, I'm gonna have the elevator accelerating upward. And then later on, look, what if it's accelerating downward? And now think about what that means. Before maybe like as I'm drawing this picture, jog your guys' memory on what this really means. So, does accelerating upward, is that the same thing as moving upward? No. Moving upward means upward velocity. That's not necessarily the same thing as upward acceleration. In fact, there are 2 different ways to accelerate upward. You guys remember that from your spring scales lab last week? The more obvious ways you could be moving up faster and faster. But what's the less obvious way to also accelerate upward? Moving down, slowing down. Yes, if he's moving down, coming to a stop, yep, that's also accelerating upward. Okay? Vice versa for elevator accelerating downward. The most obvious way would be like maybe free fall or partial free fall, like moving down faster. But what's the less obvious way to also accelerate downward? Yep, exactly. Moving up, coming to a stop. Yeah, so you want those. Okay. Let's throw our little guy in here. He's standing on a scale. Each one of these situations. Okay. And let's do a free body diagram. So FBD, you guys know, stands for free body diagram. FBD, free body diagram. Okay. Well, if he's accelerating up there, shouldn't there be a net force on this guy that's upward? So I'll put a big old center mass dot right there. And so he has some weight, it's pulling down, call it mg. Okay. Notice I'm keeping this really general, just in terms of variables, because I want to derive an equation for you guys. Okay. Actually, the equation I'm deriving right now, I would not be surprised at all if you have to also derive this on one of your FRQs in May. Okay. He's going to have a huge upward normal force. Isn't this the normal force from the scale? F sub n, normal force. Right? Versus if he's accelerating downward, wouldn't he have a weight that's greater magnitude than the scale is pushing him back up? Maybe it's like a really tiny normal force, like that. Okay, is that true? Is that okay? So net force upward, net force downward. Is that? Actually, at an extreme, he could be in perfect free fall. That would also be accelerating downward, wouldn't it? Okay. This is one of those good tools for your mental toolkit that you can get out of a class like physics. Is, what if I turn a variable all the way up or down to some extreme? Okay. If he's in perfect free fall, wouldn't the only force on him just be his weight? And the normal force would just be 0, it'd be floating around like an astronaut? So keep that in the back of your mind, because that's going to come back in a minute. Okay, so Newton's second law of motion, net force is equal to mass times acceleration. I'll set that up for each of these. And let's suppose that I just want to treat acceleration as a positive value, either positive up or positive down. I'm just doing it this way. So the first case where he's accelerating upward, wouldn't this be his normal force up minus his weight down? And that's equal to ma, right? Because that's the net force, the difference of those two. Right? Versus the picture on the right, since his weight is more than his normal force, I'll just subtract it that way. So I'll say mg minus normal force. Yeah, and that's that's if he's accelerating downward. So I've changed the direction. Okay. On the left side, it looks like up is positive. On the right side, it looks like down is positive. Okay, look at that. Okay. So if I solve for normal force for each one of those situations, well, this one's just one algebra step. It looks like mg plus ma. Okay. And over here, I have to do a double swap. I'm going to get mg minus ma. Interesting. Okay. And, oh, hey, I got two terms on the right side of each one of these. Try to factor out the mass. And you guys see that the normal force then is going to be mg plus a. Or over here, the normal force was mg minus a. Interesting. You know what I could do, I bet, is I could bring these together in like one giant master equation. I could say, in general, the normal force on this guy from this set here and from this set here is equal to mass times g plus or minus a. Couldn't you see that? Is that okay? And then once you guys see that makes sense. Because first of all, what if he's not accelerating? What if he's just like sitting there at rest, the elevator's not even moving yet? What should the normal force be? Equal to his weight. Hey, look at that. What if you set acceleration equal to 0? Isn't it just mg? It does match his weight from either perspective also. Yes, that? How about if you're accelerating upward, shouldn't the scale read more than his weight? Hence this plus. And vice versa, if you're accelerating downward, should like slack off a little bit, hence the minus. Okay? And at an extreme, you guys remember that free fall extreme situation, like a boundary condition? At an extreme, how much can he accelerate down? Maybe all the way up to g, right? Like that would be perfect free fall. Guys, what is g minus g? That's just 0, right? So you'd just be floating around. There'd be no normal force at all. You feel like an astronaut. Okay? That makes sense? Okay. So we've got this master equation here. And you know what is, even though I solved this in terms of normal force from the scale, it's also exactly applicable to if there's a tension in this elevator cable. You guys see this elevator cable here, or elevator cable right here? You think there's some tension in that cable? And if I included mass be like the whole box, like the whole elevator, it's the same story. Tension in an elevator cable is also mg plus or minus a. So it's the same equation. And you know what? You guys have actually had that equation since the first day of school. You guys remember this page right here? So linear motion, we did that. Projectiles did that. We're on to forces and Newton's laws. And I'm going to zoom in here. This is really tiny on the camera. Let me show the camera real fast. See if I can get that along right. Okay, so if you're watching this on video in the far future, then maybe take a screenshot or something. Right. But you guys were looking, hey, look, it's Newton's second law of motion, F equals ma. Here's friction force compared to normal force with the coefficient of friction. If I skip down one, I've got, hey, there's Hooke's law, F equals kx. And look at this guy right here, tension in an elevator cable, m times g plus or minus a. Right? I said, you guys have had this a while. Now, I will tell you guys too that if you get this as an FRQ question in May, which could totally be, because this is definitely an AP style question, AP would expect you to derive that equation from scratch. Like if you just write this down, move on, it probably not award you list the points. So you would have to derive that from scratch. Okay. Well, great. So we've got a formula that we can apply. Let's go back to the problem. We were given the mass of the guy, and we were given the scale reading from the scale reading. So what is the acceleration of the elevator? Let's find that out. So still number 7. So I'm going to go the normal force. That's actually what the scale reading is. Mg plus or minus a. Let's suppose this guy had a mass of 60 kilograms and the scale is rating like 700 newtons. Okay. Can you figure out, oh, and then of course G would be about 10 meters per second squared. Can you figure out how much this elevator is accelerating? Oh, well, now we derived it, we got this handy formula, just plugs up in. So divide both sides by 60 kilograms. So with 700 divided by 60, looking at 11.667 meters per second squared, which is all, hey, you guys just Newton divided by kilogram, Newton per kilogram. That's the same thing as meters per second squared, because it's an acceleration value. It's equal to 10 meters per second squared. And I'm just pointing that out because AP likes to do that. And sometimes AP will report accelerations in meters per second squared, which you're used to. Sometimes AP reports acceleration in Newton per kilogram. So you'll see both. Subtract this over. It looks like acceleration is equal to 11 minus 10 is 1. So 1.67 meters per second squared. Also called 1.67 newtons per kilogram. So same thing. So be ready to feel both of those units for acceleration. Okay. You guys good? Yeah.
Why are you dividing by the 10 instead of adding or subtracting?
Yeah, so, oh, wait, you got
It just looks the same as if you divided it.
Okay, yeah,
It's
let's
just
go through those steps one more time. So I took 700, I divided by 60. That's how I got this number. Then subtracted over the 10. Oh, I see what you're saying.
Yeah, it confused me.
Okay,
It's the same.
I see what you're saying. Yeah, okay. All right, you guys get that? I've got one more question of my own about this elevator. Suppose, I'm gonna see show of hands. I wonder how many guys didn't get this. Suppose that elevator is moving up at constant speed, just moving straight up at constant speed. Is the reading from that scale gonna be more than, equal to, or less than his weight if the elevator was at rest? It's moving up at constant speed. How many guys say that that scale reads more than his weight? More than his weight. Who says it reads equal to his weight at rest? Equal to his weight. Well, there's my winners right there. That's the answer. Because, guys, if you're moving up at constant speed, what's your acceleration? 0. And it's just, hey, moving up at constant velocity, isn't that also an example of equilibrium? Yeah. So whether you're moving up or down, for that matter, at constant velocity, it's just going to read your usual weight. Okay? That's a question that throws not only a lot of students, I've seen some physics teachers be thrown by that too. So, yeah, awesome if you got that. Next one, we've got a bullet of some given mass leaves the muzzle of a rifle with some given speed. What force would be exerted on the bullet as it's traveling along the barrel of given length? Ooh, all right, let's try this out. So number 10. When I don't know if I told you guys, but one way I got really good at physics is I tutored physics in college. Whenever you tutor people or help people out, that's one way to really learn the material well. And yeah, the college textbook, I remember, was like full of examples of guns. And it's like, wow, this could only have been published in America. True story though, it's like every other example is like, this gun shoots this gun. Well, out there. Yeah, pretty much. Right, so we've got a rifle. It's not exactly straight, but that's okay. It's gonna shoot something, I guess. I'll give this a length of, trying to make numbers that are close to, okay, but a little bit different. Suppose this is 0.90 meters long. Suppose that the bullet has mass. They reported in grams. I'm gonna have a 7-gram bullet. Guys, grams, is that the base unit of mass? No, kilograms, right? So keep that in mind. This will have a velocity of, I'll say 500 meters per second. Okay. So yeah. Okay, so that's all the numbers. So what was the blast force to get it up to that speed and this length? Okay, got some math. You know, this seems kind of like that football problem from earlier, doesn't it? If the football was kicked, we're trying to figure out, trying to figure out the kicking force like that. This seems a lot like that. So I think we're gonna have to start with the kinematic stuff again for it to speed up to the speed from rest in this distance. There had to have been some acceleration. And then after that, apply Newton's second law and say, okay, well, if you know the mass and the acceleration, you can find the force. Right. So if we're starting with kinematic stuff, or the three amigos, which one looks like it's gonna help us the best? Solve for acceleration. Yeah, the last one, for sure. See how the last one does not say anything about time? We were not told how much time it takes to go, right? But we were told the rifle length, which is a more reasonable number to know. Like this. Yeah, let's do it. Let's go. The speed it builds up to squared is the starting speed squared plus 2ax, okay? Where it built up to 500 meters per second. Square that. Started from rest, so I'm whatever that number 0. Okay? Plus 2 times a, which we're solving for. And it's all happened over a distance of 0.90 meters. Okay. So what is 500 squared, all divided by open parenthesis 2 times 0.9, close parenthesis. I'm looking at an acceleration of, yeehaw, 138,000 some meters per second squared. Looks like what about like 14,000 Earth G's, like something crazy. Okay, so that's a good midway point, but we still got to figure out the force. What was the force? So net force is equal to mass times acceleration. Remember, we had a mass of 7 grams. Isn't that like 7 divided by 1,000 kilograms? You guys remember that kilogram is the base unit. It's like baked into the cake of 1 Newton is equal to 1 kilogram meter per second squared. So I've got 7 over 1,000 kilograms. That's the mass of the bullet, base unit. And here's the acceleration. 138,000 some meters per second squared. And so what force is acting on the bullet to make all this magic happen? 7 over 1,000 times 138. Something. Is that right? 138,000. Yeah. I'm looking at 970 newtons. Woo! If you're 3 digits, then might be something like that. Yeah, there you go. Guys good? Number 11. We got a boat moving through the water. 2 forces acting on it. One is a 2,000 Newton force forward push by the water on the propeller. The other is 1,800 Newton resistive force due to the water on the boat, like a drag force. Well, you guys know there's actually 2 other forces that they forgot about. There's the weight of the boat and the buoyant force, but those balance out anyway. What is the acceleration of the boat at given mass? And if it starts from rest, how far will it move in some time interval? It will be its velocity at the end of that time. Oh, well, this looks like here's some idea of what we've been doing is combining dynamics and kinematics. Okay, so I'm gonna make it my own boat. Center mass. No, this boat, of course, has a weight and a normal force that already balance out. I'm not even going to draw these to scale other than they balance each other out, so we're just going to ignore those. We do care about there's a force that's propelling it forward, force propel. I'm going to make up my own number. Let's say this is like 3,000 Newton force. Okay? And there's also a drag force. Suppose this is F drag is like 2,500 newtons. Okay, so we got that. Right, so more force forward than back. And let's have the mass of the boat in boat be, that is 800 kilograms. So there you go. Here's the setup. First question was, what is the acceleration of the boat? So part A, acceleration. Well, isn't acceleration net force divided by mass? Get that real fast. So I'm looking at 3,000 newtons forward minus 2,500 newtons backward, all acting on an 800 Newton boat. So 500 Newton net force divided by 800, or whoops, I messed up, kilograms. 800 kilograms is the mass of the boat. Okay. That looks like 0.625 meters per second squared. Okay, so definitely looks like a reasonable number, I guess, right? So, because you guys know free fall would be about 10 meters per second squared, so that's a tiny fraction of that. Yeah, I can believe that. Next question. If it starts from rest, how far would it move in 10 seconds? Does that sound like a job for this guy right here? 10 seconds, you know the acceleration starts from rest. Let's do that. So, get new paper, I guess. Part B. Picks up to some speed, starts from rest, plus AT. Speed it picks up to is, it's picking up speed at a rate of 0.625 meters per second per passing second. And I did that for, say 10 seconds. When it pick up to 6.25 meters per second, that's how fast it's going. Okay. And the last question, hold on. Oh, whoops, sorry, that was part C. Okay, whoops. I'll do these backwards. Oops, okay, that was part C. Part B said how far did it go? So how far did it go? Isn't that 1/2 AT squared? Okay. So 1/2 0.625 meters per second squared times 10 seconds being squared. So 0.5 times 0.625 times 10 squared. Looking at about 31 meters. Not that far. Okay. That's good. Right, now we got the bird feeder question. Right, number 19. Okay, so this has all been a big kind of warm up so far. Now it's about to get more exciting. Got a 150 Newton bird feeder supported by 3 cables as shown in this figure. Find the tension in each cable. Okay. So a bird feeder of some known weight being held up by cables. If you guys look at the solution, you guys know that all the solutions are already posted to Classroom, right? I did solve this all on one page. In class, I'll solve it a little bit different way. It's probably going to take more than one piece of paper. But here, let's get this going. So there's some sealing. There's these cables that are, if you look really close, even in the setup, can you guys see a 30, 60, 90 triangle going on there? Okay. So try to draw it as best I can. About like that. Okay. And the bird feeder is hanging straight down. All right, so there's some tension. Okay.